All right, so this is the follow-up to class, the error that I made. So we're just going to go over quickly the example again, just to kind of explain everything. So we have the 2.05 megawatt fire, and it's burning, so it's 2 meters away from wherever the fire is. 2 meters over is where the sprinkler is. And then it's 3 meters above that, the sprinkler. Okay, so we've got the fire, and then 3 meters up and 2 meters over. Okay, so that's where our sprinkler is going to be. And we want to know, based on that information, what is the upper layer temperature going to be at this point for the fire. All right, we're also given the dimensions of the room, so we know that it's 5 by 6 by 3, and then it also has a vent that's 1 by 2. Okay, so we've got the compartment, and it's got one little door. And so as the fire's burning, we're going to have oxygen coming in to the door, and that's going to be the ventilation for the fire. So that's going to impact the overall upper layer temperature. And we're also told that the initial room temperature is 25 degrees Celsius. Okay, so we have to, using this, use the temperature of the upper layer formula. And so that's going to be the ambient temperature. So that's going to be the 25 degrees Celsius. And then the upper layer temperature is going to be this much hotter. Okay, so whatever the room temperature is plus how much energy is being added based on the geometry of the room and how big the fire is. So that 2.05 megawatts is going to be our heat release rate. And we have to remember the heat release rate is in kilowatts. So we're going to have to multiply that by 1,000 to get 2,050, and that's a 5 kilowatts. Then we have the HK value, which is the property of the surroundings. But we said we're just going to assume for this course that that's 0.025. Okay, so that's going to be a constant. And then we have the area, surface area of the room minus the vent openings. So just the actual walls, the ceiling, and the floor that are going to absorb the energy from the fire. And then the last part is the ventilation parameter. Okay, so the area of the vent, the area of the door, and then the height of the door square rooted. So we're going to take all that information, put it in there, and then we'll end up determining what the actual heat release rate turns into for heat-wise based on the geometry. And then we'll add that to the original temperature and figure out what the final temperature of the hot layer is. So we're going to put these values in. So 2050 is going to be the kilowatts, that's squared. The H is the constant number, 0.025. And then the surface area is, we've got 5 by 6 for the floor and the ceiling. So 5 by 6 is 30. And then we've got 5 times 3 and 6 times 3. So 15 and 18. And then we're going to multiply those by 2 because there's an opposite. So the floor and the ceiling, this wall and that wall, and that wall and that wall. Okay, so we're going to multiply those by 2. And then we take away the 2 for the vent. So we've got the vent area 1 by 2. So that is the minus 2. Okay, and then we multiply by the area of the vent, which is 1 by 2, so 2, and the height of the vent square rooted, which is 2 meters, so square root of 2. So we put all those values in, and we should end up with, drum roll, 561 degrees Celsius. Right? So the upper layer is going to be 561 degrees Celsius at this point. And so when we look at that, the upper layer is 561 degrees Celsius. And the temperature at the detector in the previous was 207 degrees Celsius. Right? So the upper layer is much hotter. And we said that sometimes we're going to expect the upper layer to be hotter, sometimes to be colder. And the reason for that is strictly based on the geometry down here. Okay, so well, I guess also the heat release rate. So how big is the heat release rate? A bigger fire, it's going to have a bigger number here. So we're going to get a big increase in temperature from whatever the ambient is. But this bottom value down here, the ventilation parameter, as well as all the surface area. So the bigger the room is, the cooler the upper layer will be because there's more space that has to be heated up by the fire. And the same with the ventilation parameter. The bigger that is, the more fresh air is coming in. So it helps make the fire bigger, but it's also cooling the room down. So the combination of those two things will sometimes cause us to have an upper layer temperature that's very hot. Other times it may be cooler than what the ceiling jet is. Okay, so it's not always definitely going to be hotter or definitely going to be colder. All right, so I just wanted to clarify that before our next class. And thank you, and we'll see you next time.